Okay, so what we're going to do is we're going to talk about Brønsted and Lowry concept of acids and bases. Acids in the Brønsted and Lowry model are what's considered proton donors. Okay, bases are what's considered proton acceptors. Now remember, when we say the word proton, what we're really talking about is just a hydrogen. Remember that hydrogen has one proton and it's got one electron. If it gives away that electron to become hydrogen plus, then the only particle left is that lone proton, right? Because the electron is gone. So in this situation, remember that this is hydrogen, and this can be called hydrogen ion, or it can be just called a proton. So if you hear me say the word proton, remember that I'm talking about just a hydrogen ion. So let's look back and review real quick the Arrhenius model. So the Arrhenius model says that an acid or a base are going to be substances that release hydrogen. Release hydrogen ions, or release hydroxide ions, depending of whether it's an acid or a base reacting in water. So let's take a look at a couple of examples here of some reactions. Now we have ammonia, which we know is a base. Okay, that's reacting with water. So when this reaction occurs, what happens is we end up with NH4 plus OH1 minus. So based on the definition, right, here is our hydroxide. So because this reaction releases a hydroxide ion, that means that ammonium must be a base. And that's exactly what we said here, right? It's a base because of this guy here. If we take a look at another reaction, right, we already know that hydrochloric acid, we already know that this is an acid. Now, the reason it's an acid is because when this compound reacts with water, right, we end up with the hydronium ion plus the chlorine ion, right? If you were to write this as a simple net ionic equation, this hydronium ion can be rewritten as just hydrogen plus, right? Because it's forming a plus ion. So because of this guy here, right, here's our hydrogen. So based on that, the Arrhenius model says that this compound is an acid because when it reacts with water, it releases hydrogen ions, right? So that's the basic definition review of the Arrhenius model. Now, what if there's no water present? What if these compounds are reacting without water? Does that still constitute an acid-base reaction? So that's what we're going to look at today. So the Arrhenius model is very narrow in that it looks at specific compounds reacting with water and looking for the release of hydrogen and hydroxide ions. This is correct, but it's too narrow because, for example, if we were to take ammonium, which we just established is a base, and we were to react it with hydrochloric acid, again, we already established that hydrochloric acid is an acid, right? So does this constitute an acid-base reaction if the resulting products, which are here, plus Cl minus, and these become positively and negatively charged to form the compound ammonium chloride, which is a solid, okay? Now, this is a result of a reaction. So what happens is ammonia reacts with hydrochloric acid to form ammonium, which is a positive polyatomic ion, and chloride, which is a monoatomic ion. Because these two are now oppositely charged, they're going to come together to form a single compound, a precipitate called ammonium chloride, right? Because now they're forming an ionic compound. You have two ions with opposite charges. Now, the question stands, right? You can clearly see that at this reaction, there's no hydrogen ions that are being released. There are no hydroxide ions that are being released. So based on that, are these still accurate, right? Is this still considered an acid? Is this still considered a base, or vice versa, right? Even though you don't have the release of those ions. Well, let's take a look. Let's take a look at what's happening here, right? Here's the Lewis structure for ammonia, right? And when ammonia reacts with hydrochloric acid, what ends up happening is this hydrogen, right, that it's given it's one electron, sorry, to chlorine, is then released and transferred over, right? So this hydrogen is going over here and it's being donated to the ammonia. Now, the ammonia, right, here is accepting the hydrogen, right? So when we go back to our definition, right, here we can see that based on the new model over here, right, ammonia has become ammonium because it accepted hydrogen, and hydrochloric acid has become a chloride ion because it donated the hydrogen. Do you see that? So based on this definition, even though, right, we don't have a release of hydrogen ions or hydroxide ions, this is still an acid-base reaction because we know that we reacted a known acid with a known base, right? But the definition changed just slightly. So what we have here now is we're kind of redefining what makes an acid and what makes a base depending on the status of whether the compound is donating a proton or a compound is accepting a proton, right? So what you have here, right, what you have here is the basic definition or the outline for a Brønsted-Lowry base and acid. So a base, right, accepts a proton, and an acid donates a proton, right? That's what's going to define a Brønsted-Lowry acid to a Brønsted-Lowry base. So on this definition, right, here we have the base because it's accepting the proton, and here we have the acid because it's donating the proton. Does that make sense? Let's look at another reaction that's in equilibrium. So here we have hydrogen cyanide, right, reacting with water. Now, in this case, we are going to react with water, but you can see that even though the definition and the model for the Arrhenius acid holds true, it also works for the Brønsted-Lowry. Okay, let's take a look at what's happening here. Let's take a look at this reaction in the forward direction, right? So here's what we got. We have hydrogen cyanide reacting with water to form the hydronium ion and the cyanide ion. Now, in this case, we are releasing a hydrogen ion, right, which goes to the Arrhenius model. But let's look a little bit deeper and let's see exactly what's happening. Now, based on the products, right, and I'm looking at the products on this side here, right, I can see which one clearly donated and which one clearly accepted, right? So I can see that this guy, the hydrogen cyanide, is donating its hydrogen here, right? And I know that because if you look at water, it goes from having an H2O to an H3O, right? So the hydrogen, right, and that's supposed to be an H plus, right, is being donated to the water. So this guy is behaving as a Brønsted-Lowry acid, and this guy is behaving as a Brønsted-Lowry base, right? Why is it becoming a base? Because this guy here is accepting a proton, and this guy is donating a proton, right? So here we can clearly see which one is the acid, which one is the base, right? Looking at the products, you can confirm which one has one more hydrogen than it had before and which one has one less hydrogen. So make a note, right? You can see that this one has one more hydrogen and this one has one less hydrogen, right? And you can confirm by looking at the products which one is donating and which one is accepting. Now, let's take a look at this reaction again, okay? But now we're going to look at the reverse, okay? Let's look at this reaction in the reverse direction. When I say the reverse direction, what I'm saying is we're going to look at it as if the direction of the reaction was moving to the left. So now we're going to take a look over here where the products are, right? And the situation's kind of changed a little bit, right? So now you have hydrogen, right, or hydronium, and is reacting with cyanide. Now in this situation, going back to the reactants, going in this direction here from right to left, right, we see that in this case, the one that's donating the hydrogen is going to be this one. So this one is going to donate here, right? It's going to donate a hydrogen. So in this situation, the hydronium is acting as the acid, where over here it was the water, it was acting as the base, remember? Now over here it's acting as the acid, and the cyanide that was once the acid over here is now behaving as a base because it's accepting that proton, right? I'm going to abbreviate that as accepting. So when you go in one direction, right, the hydrogen cyanide, look up here, is the acid. Now, when you're going from the products back to reactants, you can see that the cyanide molecule is now ready to accept this hydrogen here, and it's now acting as a base. The water, which was initially the base, right, up here, is now acting as an acid and donating this electron here, and is behaving as an acid. Right? So when you have a reaction in equilibrium that works in both directions, your initial acid and your initial base are going to swap roles to do the same reaction, but in reverse. So what we have, right, is something called a conjugate acid and a conjugate base. Conjugate acid and conjugate base basically just mean pair, right? So if I was to look at this reaction, right, I would say, let me see if I can do this in green, okay? Here we have our acid, right? And here we have our base. So this reaction here, and let me erase this real quick just to make it clear. What we're going to do is we're going to identify our conjugate pairs. So if this one started off as an acid and is now behaving as a base, this is the acid, and this would be considered its conjugate base, right? If you look at the water in this case is its base here, and now is behaving as an acid here. So if this is your base, then on the other side, that becomes the conjugate acid, right? This is the Brønsted-Lowry model of acids and bases. It depends on which one is accepting and which one is donating. Now, if a reaction goes in both directions, then understand that the roles are going to be reversed. That's where the term conjugate base and conjugate acid come from. Okay, it's the pair where once something was acting as an acid, like the hydrogen cyanide, and now is behaving as a base, like the cyanide ion. Okay, so let's take a look at another reaction and let's practice a little bit. Right now, we can see here that we have our carbonic acid here, or hydrogen carbonate, reacting with dihydrogen phosphate. Right now, when we look at the products, right, it makes it a little bit easier to see which one is being donated or is doing the donating and which one is doing the accepting. So let's take a look at the number of hydrogens, right? So I'm going to underline these here so we can do a little bit better. This one has 1 hydrogen. This one has 2 hydrogens. This one has 2 hydrogens. And this one has 1 hydrogen. So you can see by the decrease or the increase in the number of hydrogens, which one is being donated and which one is doing the accepting. So based on this, I can see that this one is going to accept and this one is going to donate, right? Because I can see that the dihydrogen phosphate decreased from 2 hydrogens to 1 hydrogen right here. Right? So I can see that this one clearly donated a hydrogen proton. So what happened in this reaction, right? This guy is donating a hydrogen here. Okay. Now, based on this, I can see that this is going to be my acid. And this one's going to be my base. Okay. So what we're going to do now, right, is we can see which one is the acid and the base. And on the other side, we're going to identify the conjugate pairs. So if this is my acid, right, this is my acid, then this one here, the hydrogen phosphate, right, has to be my conjugate base. This is my conjugate base. Now, if this one, which is the hydrogen carbonate, right, if this one is my base, then on the other side, this one is going to become the conjugate acid. And that's how you identify the acid, the base, and its conjugate pair. Now, looking at certain substances, right? Certain substances are going to be considered amphoteric. Amphoteric means that a substance can behave or react as an acid or a base depending on what it's reacting with. Now, water is the most common example of an amphoteric substance, right? So let's take a look at a couple of reactions here. So if I react water, for example, with hydrochloric acid, right, which we know is an acid, then in this case, water is going to behave as a base. You can see here, because based on the number of hydrogens, right, we can clearly see that this guy is donating its hydrogen here. So this guy is behaving as an acid, and water is going to behave as its base. Right? So if I was to sit here and identify the conjugate acid, you can see that clearly on the other side, this is going to now behave as an acid, right? And this one over here, which is the hydrochloric acid, this is the acid, and over here, it's going to react as a conjugate base. Okay. Now, remember, this is assuming that this equation is in equilibrium. So if it goes back in this direction, this would be the acid, and this would be the conjugate base. So here you can see that water is acting initially as a base because it's accepting that proton, right? Now, if you were to take another reaction, right, and react water with ammonia, for example, well, in this case, water is going to be the one that's going to donate this hydrogen over here to ammonia, right? So in this case, water is actually behaving as an acid, and the ammonia is behaving as the base. Same thing, as this reaction is in equilibrium. If this is the acid, then the conjugate base would be over here. So this is your acid, here is your conjugate base. With the base, right, this one is your base. You react it over here. Now it becomes your conjugate acid. right? Because what's going to happen here is the ammonium is going to take this hydrogen, one of these hydrogens here, and donate it back for the reaction in the same in the reverse direction. Okay, so water is an example of an amphoteric substance because it's able to behave both as an acid and as a base depending on the compound that it's reacting with, right? Now, the ability for something to behave as either as an acid or a base, right, can also be called, let's see here, let me write it in blue. Its properties, I'm sorry, can be called ampho. Sorry, amphiprotic. So, for something to be characterized or its ability to behave in an amphoteric manner is defined basically as its amphiprotic properties, right? So this goes to the ability to be amphoteric. All right. So in summary, when you're looking at the Brønsted and Lowry model of acids and bases, okay, the Brønsted and Lowry acid is going to be the proton donor, and the Brønsted and Lowry base is going to be the proton acceptor. Okay, and this is basically just looking at a reaction and seeing where that proton is moving and determining which one is doing the donating, which one is doing the accepting. All right, thanks guys.